that it's hitting has basically this area. And that area is equivalent to L squared. So let's just say we were just talking about this. This is the L we were talking about in the x direction. The size of the container, if it's a cube, is also going to be L times L. In general, it's just an area. So pressure is force divided by area. Well, that's going to be equivalent to mvx squared divided by L squared times L. Where the L squared is from the area, and that other L is from here. And that just gives us now the pressure is mass times the velocity squared divided by L cubed, which pressure then is mvx squared divided by the volume. Let me capitalize that to represent volume. Now, I should say for a distribution of gases, for a strict distribution of gases, we cannot use Vx. We would have to use the average velocity of the gases. And average velocity is also given as v bar. So I'm going to replace velocity with average velocity. And thus, the pressure really for a distribution of gases is going to be m v bar x squared. So once again, I'm only talking about the x direction, divided by the volume v. So what I've been able to do right now is I've been able to relate the idea of pressure in this container to now, once again, as of right now, I'm solely looking at one dimension. I'm only looking at the x direction. So that's what I've constrained myself to do right now. I'm only looking at the velocity in the x direction, but I know that it's a three-dimensional object. Clearly it has to be. We live in 3 dimensions. And to make life as simple as possible, because volume could be any shape, but to make things as simple as possible, I'm considering it to be a cube of size L by L by L. And thus the surface area, when it hits the wall of the container, is L squared. And that's how we were able to get this volume. Well, moving from this, so this was when we have a distribution of gases, we have to take the average velocity, not its actual velocity. Now let's say we have n molecules in this distribution. Because of this, let me drop this little line right here. We'll see why I can do that now. Let me call the pressure due to n molecules that are all moving in the x direction. So I'm still only saying it's in the x direction, but now I'm saying instead of just one of them, I'm having n values moving back and forth. So n molecules right now. If I do that, then the pressure from n molecules is just going to be n times the pressure I found for one of them. Because it's the same general equation. If I'm now using their average velocity, now I'm saying all of the gas particles n have an average velocity, so I averaged it out. They will all relate to the same value. So now, the pressure due to n molecules in this distribution is still solely only looking at the x direction, just becomes n times that pressure, so n times m, the average x velocity squared, divided by the volume, or let me rewrite this as n divided by the volume of the container times m, velocity in the x direction, squared, average. But of course, life is three-dimensional, so now what I want to go to is 3 dimensions. Let's go 3D here. And by going 3D, let's remember something about velocity. Any vector. So this gets to the idea of vectors, which is the same idea as Pythagorean's theorem. So let me just write out in vector form, so this gets back to what we learned in the beginning. Velocity in 3 dimensions is Vx, x hat, plus Vy, y hat, plus Vz, z hat. If I wanted to find the velocity squared, which is now just a scalar value, then what I'm doing is I'm doing v vector times v vector, And remember, x hat times x hat is equal to 1, y hat times y hat is equal to 1, z hat times z hat is equal to 1, but x hat times any other, or y hat times x hat or times z hat or anything else, if they're different unit vectors, they equal to 0. So this says the velocity squared is just going to be bx squared plus by squared plus bz squared. Now let me also take average. So the average velocity squared is just equal to the average x velocity squared plus the average y velocity squared plus the average z velocity squared. And now let me say, since I'm making everything ideal and saying the volume of the container is a perfect cube, and let me say that there's no gravitational or any other type of forces which are preferentially disturbing or accelerating the gases in one direction. If none of that exists, if it's an ideal situation, then we can say Vx is equal to Vy, which is equal to Vz. And if I do that, what I now say is that V squared is equal to Vx squared plus Vx squared plus Vx squared, or 3 Vx squared. So I now have just gone to 3 dimensions. So V squared is equal to 3 Vx squared if there are no forces which are accelerating the molecules in any of the dimensions. So what does this mean? This means that V average x squared is equal to 1/3 V average squared. Now let me put this value into here to find out what the pressure is going to be in a distribution of n molecules in all 3 dimensions. And if I do that, let me call it P3n, where this represents 3, the number of dimensions, x, y, and z, so an actual 3D volume. N is representing n molecules, so not just 1. And if I do this, this gets me to, of course, 1/3 n molecules divided by the 3-dimensional volume V times the mass. Let's consider that it's all the same molecule right now. So molecules are the same, so we're just dealing with, say, oxygen, or just dealing with, say, hydrogen, not, say, nitrogen gas and oxygen gas like air. All the same molecules. M times the average velocity squared. Well, this is important. We could even box this off right now. It's so important. But notice I called this, or titled this, the kinetic theory of gases. We remember what kinetic energy is. Kinetic energy is 1/2 mv squared. And thus this value of mv squared, mv average squared, is equal to twice the average kinetic energy. Where remember, the bar always means average. So here I could also write this as the pressure of the 3-dimensional space of n molecules is just going to be equivalent to 2/3 the number of molecules n divided by the volume of the container V multiplied by the average kinetic energy. Or if you didn't want to leave it like that, 2/3 n divided by V, if you just want to leave it in terms of 1/2 mv average squared. But it means the same thing. That the pressure in a 3-dimensional object, so in a real object, when we're talking about gases and a distribution, so we have to deal with average velocities of n molecules, is equivalent to 2/3 the number of molecules n divided by the volume, and thus multiplied by the average kinetic energy. And this is where we start to see the bridge here. This is what we're talking about. Kinetic theory of gases refers to the fact that we can relate the pressure of that gas to the kinetic energy of that gas as well. So of course, n is just a number. We could, if we were able to, count up all of the molecules. V is a macroscopic value of the volume. And here, kinetic energy, this is how we're relating to. So pressure is related to energy. And this is why when I said it was really, pressure could be related to as a vector, we don't really use it as a vector, because here it's in an easier way that we're relating it to a scalar quantity. But for right now, I will go over this greater in next class. But all of you have already seen this, the ideal gas law. This will help us relate to temperature. One of the ways that the ideal gas law is expressed is pressure multiplied by volume, PV, is equal to N, the number of molecules, times K, which is known as Boltzmann's constant, and multiplied by T, which is the temperature. So for right now, let me just write temperature, because that looks very similar to the period T, or torque, or anything else that we've discussed.
Is that analogous to R? Because I think in Gen Chem they said PV equals NRT.
That's PV is the little n, capital RT, where little n there is not the, this is the actual number of molecules. This is the molar number.
Oh, so that the big N would be 6.02 times 10 to the 23rd, and the little N.
No, the n right there is the actual number. So if I count up every particle, n there would be related to, this n is 6.02 Avogadro's number times the number of molars.
Okay, I see.
So this is just molar quantity. If you want to do chemistry, use that, but for right now we're going to use big N because that's easier, so the actual numbers. So doing that for us, just quoting this right here, notice what we have. We have a relationship between pressure, and here we have pressure once again. So what I'm going to do right now is just PV is equal to, let me input this value of pressure. Let's see, I'm going to input this value right here. So I'm going to input this value here. So that's just going to be 2/3 n the total number of molecules times the volume V times 1/2, or the kinetic energy, 1/2 mv average squared times the volume. That's equal to nKT, the temperature. And what do I see here? On the left-hand side, volume cancels out the volume. On both sides of the equation, we have n. So the number of molecules cancel each other out. That's why I'd like to use n here, just because we use n in the derivation of pressure. We would just have to do a couple more steps to get that to be little n, the molar value. But by doing that now and crossing these out, we can now relate what temperature is. Because now what we have is, let me also see right here, I'm going to now multiply this, so I have 2/3, 1/2 mv squared, so the kinetic energy is equal to kT. Or what I could say now is 1/2 mv squared, which is equal to the kinetic energy, the average kinetic energy is equal to 3/2 kT.
That PV, it's volume, right?
Yeah. So I now can say the kinetic energy, the average kinetic energy of n gas molecules is related to 3/2 a constant, Boltzmann's constant, multiplied by temperature. And this gives us what temperature really is. Temperature, specifically for a gas, but in general, is now related to mv squared, average velocity squared, divided by 3k, which is just equivalent to 2 times the average kinetic energy divided by 3k. K is a constant. But notice what we see here. It's a constant with different units, which changes from joules to, say, degrees Kelvin, which is the scientific unit. But notice what we're saying. Temperature is equivalent to kinetic energy. Unless this is something that people stumbled on but did not understand, that heat, which we'll learn more about, is a form of energy. And thus heat transfer, say heat going from a hot object to a cold object, that's a transfer of energy. And thus temperature is what measures heat. And what we see here is that temperature for a gas is actually 2 times the average kinetic energy divided by 3 times a constant, Boltzmann's constant. So in this room in particular, how could we find, in this case, what the temperature is? All we have to do is find what the velocity is. The velocity of gases, if the velocity of the gases increases, so if the velocity increases, that means the kinetic energy increases, which means the temperature of this room increases. And thus, the faster these gas molecules go, the hotter things get. In terms of solids or liquids, it's not actual translational movement. In that case, it's vibrational movement, such as us for a solid. It's the vibrational movement of our molecules. And the concept is that at absolute zero, where there is no temperature and thus no heat, there is no kinetic energy. No kinetic energy means there's no velocity. And that's what the idea of absolute zero is. No motion, no translational motion, no vibrational motion. And lastly, if you want to find the velocity squared, just do the rest. It's 3kT divided by m. So if you dealt with the gas, that you knew what its mass was per molecule, you could just deal with this mass m here, temperatures there, and you could find velocities of everything. But that's just because it's related to this type of kinetic energy. Okay, so ideal gas law is for us. In your recitations next week, I'm going to go over a scenario of stellar formation, which basically, quiet down guys, which basically refers to the idea there that you're going to have 2 competing forces, temperature, which is related to kinetic energy, and gravitational collapse. And in those recitations, I will show you that, in fact, it requires there to be a minimum temperature. That temperature has to be cold, and thus a small amount of kinetic energy, so that the gravitational potential energy wins and actually collapses a cloud to form a star. So that's what I'm going to talk about in each of your recitations. So one last thing before you go. If you haven't already, drop off homework 5 here. I have now put homework 6 on Blackboard. It's just a few questions. I think there's 10 total questions from 2 chapters. It'll be due next Thursday. It's on material we've already talked about here, here, here. And also,